do your best. DC circuits, so far, the current is relatively constant, except for when the circuit is being switched. Unless the load is a variable load, then the current will change. But if it's a relatively constant load, it's just going to be that DC. 13, I said. Yeah, we're gonna go to 13 and 14 and then go back to capacitance after. It's better to keep the inductive stuff together. They should have done that in the book, I think. In AC circuits, the current is continuously changing. Agree?
Yeah.
I hope so.
Show myself out.
So I'm gonna look at the current. I'm gonna use the red for the current. In the circuit. I'm not using the voltage here, we're using the current. Because the current is doing all the changing in the circuit, the voltage is causing the current to flow, right? So the voltage initially causes the current to flow. So now if we focus in, the way to understand inductive effects on an AC circuit is to look at the current. Don't look at the voltage. And if you look at it from the point of view that I'm in the current, what am I doing, right? Something is going to react to that current. So every action, there is a reaction, right? So that's where reactance comes in. It's reactance. What type of reactance? It's going to be inductive reactance because it's an inductor. So we know the properties of an inductor, that it opposes a change in current. So whenever the current is changing, there's going to be an opposition of some kind. When the current is not changing, no opposition, right? So that's basically in a nutshell how to describe what's happening in an AC circuit. So with pure inductance, if you had a pure inductor, is that possible? No?
Theoretically.
No. But you can have one really, really, really close to being pure. They say that, well, we'll get into that after, but when the resistance portion is like 1/10 of the reactance portion, we will get into that. But it's like 10 times reactance over resistance, then they consider it to be pure, because, and we'll show an example later why that is, okay, because it's so small of an effect. So let's say that for argument's sake, there's no resistance in the circuit. We're just going to look at this as if it's a pure inductor. Is there any IR drop?
No.
No.
No. So at any instant, the voltage drop across the inductor must be equal to the source. The voltage in the inductor is really a self-induced counter EMF. It's a counter EMF in the inductor. It's not a drop like in a resistor where you drop the pressure because of dissipating some energy. The energy is stored, and that's it. And then we'll find out what happens to that energy. Equal and opposite. So we've got this going on here, guys. Say that's the source. Counter EMF. Okay. I'm going to leave that there, and we'll develop this a little further, just to sort of help with this thinking. And you're going to understand this. Just keep telling yourself it's not hard. It's more of a timing issue. All it is timing, right? So far everything's been, it's here, it's all here. Now part of it's not there. It's like it's all about when is it going to be there. It will be there, but when, right? That's all what it's about. Okay, so let's look at this. Okay. Okay, scary. Current and voltage vary in an AC circuit. So Okay, let's just look, they go E applied, okay, E applied, so that would be E source or E applied, same thing. The applied voltage and the counter EMF are 180 degrees out of phase with each other. They're equal and opposite at any given time in the circuit, correct?
Yes.
Okay, so if I look at any point on the graph, let's not look at the current, let's pretend that it's not even there, just this voltage and the counter EMF is a dotted line. Okay, so voltage is 0, counter EMF is 0. Voltage is maximum, counter EMF is maximum. So that would be 180 degrees out of phase. Just like on the oscilloscope, when you guys saw those two waveforms and they were 180 degrees out of phase, they crossed the x-axis at the same point in time. So easy, 180 degrees. This would be the vector or phasor representation of that, of the two, of the source, applied voltage, and the counter EMF. Now, let's look at it this way. Now, so put this on hold. I'm going to leave that there. Let's look at the current now. And what I'm going to do is I'm going to shift this over to here and look at, let's focus on the current and what happens around it. So the current is now flowing in this circuit. If there was no voltage, there would be no current. But this has been running for a while, and we're taking it now at a point in time and say, okay, right now the current is 0. What kind of a change in current is there right here? Maximum change or minimum change?
Maximum, right?
Maximum change. So this current is changing at the maximum rate. Maximum change in current. What about when it reaches the peak value? That's at 0 degrees. What about at 90? The current level is at maximum. Let's say it's 17 amps peak.
It's like the least change.
0 change. Let's say 0. 0 change. Delta I. What about when it's decreasing? Right here at, what is this degree level?
0.
What degrees level?
180.
180, okay. So at 180, it's decreasing, but the most rapidly at that point. It's a maximum change though. Now it just switched directions. So in a negative direction, at 180, it's still maximum change. So this part here, where it's dropping down rapidly and then reversing direction and increasing rapidly in the other direction, is right when the current is 0, but it's changing the fastest. So if it's changing, then what's happening to the magnetic field? You could draw a magnetic field wave right over top of this current, with maybe a small little bit of lag because of hysteresis, but it would basically be following this current path. Okay, how about here? Now we've reached negative peak. I'm at 270. Yeah, 0 change. 0 delta I. And then now we're decreasing, but most rapidly right here at 360 or 0 again, which should be the maximum change. So looking at this from the point of view of the current, now we can say, okay, I know one thing about induction. The maximum voltage, electromagnetic induction, will be at maximum when the current is changing the fastest. So that means that the induced voltage in the inductor will be at maximum when the current is changing at maximum. So if I look at the induced voltage as the blue here is the counter EMF, I say, okay, this one here will be at maximum, but it will be in opposition to the current. So you can see what they've got there, but I'm just going to sort of reason on it with you, that this voltage level, if I extend this up, would be right here, at maximum. So if this was negative 170 volts. This was negative 17 amps. And this is positive 17. And then way up here, positive, if we call this the positive alternation and the other one the negative alternation, then we can see that. Okay, does that make sense? Current is changing the maximum right through the x-axis when it is zero current. Even though it's 0 amps, it's changing the fastest. So the counter EMF will be at maximum, has to be there. Has to be there. The current's changing the fastest, get the most oomph right there of blocking it. That's why it's 0, actually, right? Okay, so, anyway, but everything else is reacting because of the current. So that's how you got to think of inductive reactance, that it's the current and what happens because of the current changing. All right. What about at 90 degrees? What's the counter EMF doing?
0 change.
0. No change, no counter EMF. Let's go the other direction. Say, okay, I'm at 180, the current's changing fastest, but it's in the other direction. It's falling and then increasing in the other direction, so it must be way up here, at maximum, the counter EMF, right? Current's changing the fastest, it has to be in the opposite direction to that change, try to prevent it from changing. And then here at 270, no change, no counter EMF. And then we go to the last spot. Where is it? Yeah, you just basically follow it, right? Yeah, it's going to be down here, 170, and it's going to be 360 degrees. It's going to be maximum change, maximum opposite to the change, trying to oppose that change, always preventing that change. So then I just basically draw what if you plotted all the points, you would end up with something, and it's not very good. It's supposed to go through the center of that.
Oh, jeez.
Kind of like that. There's your counter EMF. So we're approaching this backwards, and there's a reason, because it helps you to understand it. Because there's always, well, I don't get, well, if there's no voltage, then how come there's all this current? Well, you got to look at it as it's already been running, and this is a point in time when you say, what's it doing right now? It's kind of like that. So I say, okay, the current's changing the maximum counter EMF. No change in the current, even though it's at 17 amp peak. 0 counter EMF. What is the applied voltage in relation to the counter EMF? Is it, what is it? Is it, how many degrees out of phase is it?
180.
How do I draw that on here?
That's 90.
Wouldn't it be opposite at every point?
Yeah.
Here. Well, there is 0 at the same point, so I know that. And then this one is down here. This one is up there. If you end up with this, that's hard to draw. There we go.
Sure. Yeah.
And I'm not drawing this part. These are supposed to intersect at the same point through the peak there. Anyway, didn't quite draw. Okay, so that's how you end up with that. So what you're gonna find is this helps you to understand what's happening. First, you have a current. When that current is changing, you have an opposing voltage induced into the inductor called the counter EMF. So you draw that, and then you say, what was the applied voltage compared with the counter EMF? 180 degrees out of phase. It's like the third step. Then you look at it from the point of view of this diagram and say, okay, the applied voltage is here. What's the current doing in relation to the applied voltage? Lagging by 90 degrees. So first the applied voltage comes, then the current comes 90 degrees later. It's like it passes the pole of the machine, and then the current comes after. It doesn't happen at the same time. It's always out of sync. And that's really what's happening here. How's that?
The counter EMF is this guy.
If you look at this,
It says counter
here's what they do, And I encourage you to read through at all the degree levels, and it's just going to say exactly what I've said here. 90 at 90 to 180, at 180, 180 to 270, 270 to 360, and then at 360. So all these words were that. So, phasor representation.
And the counter EMF is countering the voltage. That's why it goes in the opposite direction.
That's it. And you can draw the little right triangle if you want. So in a purely inductive circuit, purely inductive, because we're talking about pure no resistance, the current lags the applied, or AC circuit, the current lags the applied voltage by 90 degrees. Eli, if that helps you.
Ooh.
Voltage, current. Current comes after, so it lags. Right? And use L for inductance. There you go. Eli. You know anyone named Eli? There you go. That's Eli.
His name's actually Ellie. It's really strange.
Ellie?
Yeah, it's with a Y. He goes by Eli.
What's my?
He's Ecuadorian.
L-L-I-E. It's too complicated. Anyway, so the current lags the voltage. So if you're reading, you read from left to right in our language. So current voltage is first, current is second, so the current lag. And L means inductance. That's a good way to remember it.
When does the Iceman come?
Oh, you leave that Iceman alone. That's my the other part of that explanation. We're going to do that Thursday.
Oh, I can't wait.
Inductive reactance, okay. In a purely resistive circuit, current and voltage are in phase. So how would I draw in phase? See, you guys are in a good position because you've seen the oscilloscope. Sometimes what they'll do is the constructors will cover all this information and then do oscilloscopes later. I think it's best that you guys saw what was happening with all these waveforms ahead of time and how to use the equipment. Right? Personally, I think it's a better method. But whatever, whichever the case is, you know what's in phase, what's out of phase. You know how to read these things. Like, this looks a little complicated only because I started adding more stuff to it, right? But what's in phase? If I have an AC circuit, that's this one here, I'll just do this one. With just resistance. This ammeter easy numbers. How many amps is that?
10.
I didn't want to pull up a calculator. Okay? 10 amps. Okay. So looking at that, I'm going to say, okay, the voltage is 120 volts. So 170, negative 170, right? The current is in phase, the applied voltage. So if that's 10 amps, what's the peak amps?
0.73.
No, maybe not 17. 14?
Yeah.
Whatever 7
14.14.
Oh, no, I know it's
Yeah, I could have 14. Let's change it up.
5.7. Yeah, 14.1.
Oh, yeah.
Yeah. Where do I draw the current? Do I draw like this?
Draw it under the same
They
side.
cross zero at the same point?
Yeah.
Do they go the same direction?
Yeah.
Yes.
Yeah.
That's what's happening in a purely resistive circuit. You apply applied, I'll use the same terminology that they did. So the applied voltage, the current is in phase with the applied voltage. It's working together. Working together, so when the voltage increases, the current increases, and the voltage decreases, the current decreases, and they're riding along together, they're working together, they're getting more work done because they're not out of sync like on a wire pull or something. They're in sync, you know, when one guy's pulling, the other guy's feeding. It's just perfect, right? The job is great, you know? Until one guy gets out of sync. I feel like this one.
Until Jeff comes along.
Okay. Inductive reactance is exactly what it says. It's reacting. It's reacting to a change. So if the current is constantly changing, we looked at this from the point of view of the current. If the current is constantly changing, then the opposition to that is always there. It's always opposing it. It's continually changing. It's always opposing. It's reacting, acting, reacting, acting, reacting constantly in every case. So really, there is a value of opposition based on how fast this happens. So let's say at 60 hertz, it's going to happen 60 cycles a second. The current is changing, so the counter EMF is also changing at 60 cycles per second. But if I put it up to 120 cycles per second, or even faster, now there's more opposition because the change is quicker. It's a quicker change. Or if I slow it down to 2 hertz, 2 cycles per second, or let's say 1 cycle per second, 1001, 1002, 1003, then there's very little opposition. It's not happening as fast. So that's kind of the way to think about, with AC, the only thing about the rate is the rate of the supply of the generator that's turning and making the voltage to begin with. So the idea here is inductive reactance can be treated like ohms. In a nutshell, they figured out that a certain formula can be used, depending on the frequency, to say how many ohms of opposition that would be if it was like resistance. Because it is an opposition, and the only way you can really find that is I take this, put it into a circuit, and I'm measuring 10 amps at 120 volts. So, okay, I got my ammeter, I got my voltmeter, and I use Ohm's law. Oh, that's good. The current here through the inductor is equal to the voltage across the inductor divided by the reactance of the inductor. And I'm going to say, okay, I don't know what this reactance is, but I do know that I have 120 volts and 10 amps. So I can do this. Wait for it. Instead of R, you got an X here, right? Okay, so you're going to go 120 volts over 10 amps. Oh, that's a tough one. 12 ohms. So I have 12 ohms of inductive reactance. So when you get to AC, you don't worry about the henries, you don't worry about all that. You just know that it's so much opposition to allow that much current to flow. In ohms, opposition in ohms. That's it. It's really simple. So this is why I'm doing this now. Because we need to do a couple labs tomorrow after our quiz, and if there's any questions on this in between that time. So 12 ohms. Is that opposition, is that current in phase with that voltage flow? This is a pure inductor. Is there any resistance in that circuit? No, that's not resistance. There is no resistance. It's a pure inductor, which means there's zero resistance in the circuit. R equals 0 ohms. But why is it only allowing 10 amps to flow?
Because of the opposition.
It's the out of syncness of the current and the counter EMF that's only allowing that current to flow. It's just the way to put it, the best way I can put it. It's the reacting, it's the action is the current, and the reaction is the counter EMF. And because it's always out of sync and it's always opposing, depending how fast that happens, really slow or really fast, would mean a different number of ohms in the circuit. If it happened really slowly, then we'd have less opposition and lots of current. If it happened really fast, we'd have lots of opposition and very little current. So it all depends. Like aircraft, they use 400 hertz because they can reduce the current level down because it's always opposing, right? It's always opposing, so the ohms is more, and it's not resistance, it's reactance. Okay? In some devices. Now the device, everything has to be made for 400 hertz as well. So the wiring could be smaller.
How do they control the frequency?
Well, they have their own alternator system, right? On an airplane, just like in a car.
Oh, yeah.
Yeah, so.
Wait, airplane?
Okay, and then they say, okay, here you go. An AC circuit has an inductive reactance of 1 ohm when an alternating current effective value of 1 amp flows through and creates an inductive voltage drop with an effect value of 1 volt across the inductance. So there would be 1 volt drop if you measured with your voltmeter across this guy. You have 120 volts. Effective, so we're just dealing with effective values, not peak values. I just wanted to show you, remember what's happening to the waveform, and the effective value of all this was what, 120 and 10, roughly? Roughly. Okay. Here's one to remember then. No effect. What does that mean? Instead of me talking, we're going to get someone to pay attention to what your book says. Can you guys read it that far?
Yeah.
Close your eyes.
The AC voltage has no effect on the inductive reaction.
So what if I have 240 volts instead of 120? That's basically what they're saying. Doesn't matter. Yeah, exactly. Because it's the rate of change of current. It's not the amount of current, it's how fast the current is changing. So it's everything to do with the speed of change rather than the actual values themselves. Make sense?
So reactance is like, it's only depending on the hertz of the frequency? Is that how I put that?
Yeah, very much so. So it says, okay, well let's try that theory and say, okay, the applied EMF is doubled, the maximum rate of change in current also must double. Oh, well if I have 240 volts, if the applied EMF is doubled, the rate of change in current must also double in value, so that would mean that the opposition would be the same. It's like if I put 240 volts here, I would have 20 amps. So what's the ohms? Still 12 ohms, right? It doesn't matter. It's the rate of change. It's the frequency. There you go. Inductive reactance is directly proportional to the frequency of the applied alternating voltage. Okay, so I'm going to put 60 hertz on here now. Say at 60 hertz, I'm developing how many ohms of opposition in the circuit? In that example on the board. Let's see, what did we get? 12? Yeah, we got 12. We used Ohm's law, we got 12. Instead of R, we used X. What type of X? Inductive reactance, XL. L always refers to inductance. Okay, so that means that at 60 hertz, I'm developing 12 ohms. So the inductive reactance in the circuit, XL, is directly proportional to the frequency of the circuit. So that little fish thing means directly proportional. Right? If I had 1 over something, it would be inversely proportional, right? Okay, so applying that, and some other things about radians and all this other stuff. Okay, inductance. Okay, I'm going to just go a step at a time. Inductive reactance is directly proportional to the inductance of the circuit. So that's another true statement. So the bigger the inductance, more number of turns, the higher the permeability, the greater the cross-sectional area of the core, the shorter the length of the core, then I'm going to get more inductance. If I change any one of those things, if I buy a new coil, it's going to have a different amount of inductance, so it will have a different reaction to changing current. So it'll have a different amount of inductive reactance. So that's directly proportional. One increases, the other increases, one increases, the other decreases, right? That's what it's saying there. Right there. Okay. So here's the formula in a nutshell. XL equals 2 pi F times L. So we've already established that we've got frequency and inductance that are directly proportional. The product of those two things makes up inductive reactance. With a little 2 pi in there, just because in a circle, in a complete rotation, if you start at 0 degrees here and you go all the way around, what do you have? This is pi. If you measure the difference, it's the distance of the circle. This distance here would be pi times the radius, right? And a full circle would be 2 pi. Anyway, so it's doing a full cycle.
That's the wrong number. That's the wrong number either, right?
2 pi.
That's great.
So 2 pi radians, in other words, 2 pi distance around the circle is how that's arrived at in the formula. But you just have to remember the formula. It's like, why is it 2 pi? Well, that's 1 pi. To me, that's only half pi, but that's 1 pi. But then the other one's 2 pi. 2 pi times r gives me the area, right? No, it doesn't. The circumference. Okay, let's give some examples. So XL equals 2 pi frequency times inductance. That's the two things. 2 pi is just a constant number that's because it is what it is. C'est que c'est. It's French.
Is that going to be on the quiz?
Assist, cross assist. There you go. Okay, you guys don't find me funny. That's fine. You know what? I don't really care if you find me funny. I want you to learn. That's what I'm trying to do. So, power. Who's got the most power? Who's got the most power? This guy?
Hi, Joe.
This guy. They got the same amount of current. They both have 10 amps. They both have 120 volts in that circuit. Which one has the most power?
The one on the right.
No.
Wrong. One on the left. Wrong.
The one that's pure resistance. Pourquoi?
Porque. Fuck, man, I don't know, dude. I've only done this once before.
All right. I squared R.
Yeah.
What is that?
Power.
1200 watts?
Yeah.
What?
What?
Yeah.
I square
Energy dissipation. It means that it sucked it from the source and changed it into something else.
Oh,
Heat, right?
Oh,
Definition for energy dissipation in an electrical circuit.
This is on their last test.
0.5 squared over.
No, indeed, but there's a word for it. You know.
True power?
Oh, is it because you guys want from True Power?
This might make
There's
sense.
one that's.
All the stuff's gonna come together for you.
We have never
Um,
talked about true power.
Energy dissipation.
Is it because you're not Yeah.
I think that was where it has to do. I think that's
I'm
what
gonna
it has to
magnetize this coil,
Yeah.
store it there. Problem is, the current isn't steady anymore, the current is going back down, so the energy goes back to the source. Now, the current is increasing again, so it's storing it back in the magnetic field, and now it's decreasing again, it's going back to the source. So that magnetic field is building and then collapsing, building and then collapsing. You're storing it in the magnetic field, the energy, and then it goes back to the source. So does it really go anywhere out of the circuit?
No.
No, it's just used in the circuit, back and forth, tanks, back and forth, back and forth, back and forth, back and forth. You're playing catch, basically, inside the circuit. So the energy is not being sucked out of the circuit, the energy is staying in the circuit, if there's no resistance. If there's resistance, then whatever resistive part is doing that.
I figured out what it was. It was effective resistance.
Oh, okay, yeah.
Yeah. That was good. You're welcome, boys. You're welcome.
Okay, I'm just getting to this and then we'll do a couple calculations, just a couple brief ones. Power is simply the rate of transfer of energy. So depending on what type of power, whether you're transferring it out of the circuit or whether you're transferring it to a different part of the circuit and then back again, you're transferring it, energy's being transferred. Different forms, we've learned about the law of conservation of energy, right? So if it's not going anywhere else, it must be going back into the circuit somewhere. It just has to be, right? So when power has a positive value, the source is supplying energy to the load. So in the case of this circuit, when the current is positive with the voltage, that means this resistor is dissipating energy at that point. So let's see. Positive volts times positive amps, positive, 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 right? All positives. What kind of power are you going to get out of this? Positive power. In phase, that is the power in the circuit. Okay, now we got negative volt times a negative amp, negative volt times a negative amp, negative volt times a negative amp. At every point, positive power. Yes. So that's a.
You can never get negative power.
That's
More people.
nasty here.
Wow.
So that's what's happening. That's what's happening to the circuit. It's constantly dissipating energy, positive values of energy, to the load. And it's gone. You have to recreate the source. The source has to replenish itself constantly to provide for that, and that energy is being dissipated out to the load. Okay, so energy is sucked out of the load and thrown somewhere else. Okay. When, in the case of an inductor, I'll have to redraw it. This is very... We're going to do the same, we're going to do this circuit here. Same one.
On the quiz tomorrow, do we need to draw anything? Like, do we need to draw?
Probably not.
What learning
You
task
have
have
to
we
always
done?
draw yourself a circuit. How's that?
Okay.
Seriously, wrong.
Cheat yourself.
So important.
Okay. So I'm gonna say Eli here, right? So voltage current. So let me draw the voltage first this time.
Ice man is really the capacitor. I think that's.
Okay, there's our voltage. We have the current. Where do I draw the current? The current does what in relation to the voltage?
Opposite.
Legs it?
Which one?
Legs, so which, over here,
Going.
Further down.
No.
here?
Yeah.
Okay,
Sure.
so in time, it happens second.
Sure.
Okay, so that means it's gonna do this, right?
Did it tell you that? It wasn't in there?
We used to know it.
Right?
But then why the other dude didn't know?
So when the voltage is at zero, the current is at maximum, right? It's always opposite.
So in
Counter
case
react-
one was just like to show us how it looks, I guess.
Do you ever
No.
think of circuit?
A little bit more. Is it?
My brain's
No,
going
it's
power
like-
on.
The first
Trying
one
to
was right, but that circuit, and next one was that circuit, right?
Okay, I'm doing, isn't it 10 amps?
No, that's not what it said.
No, he's.
Oh, okay.
No, I was just confused.
The first one was really was that circuit.
Okay, yeah, thank you.
It's all good, Rhonda. I'm there now. I'm there now.
Oh, Rhonda? Yeah, yeah.
I know, it's good that we make the connection, right?
Yeah,
Yeah.
just a little slow to get there sometimes.
I'm gonna still put the 60 hertz there because I'm leading somewhere else with that. But just put that on hold.
Foreshadowing.
Okay, so we got voltage, we've got current, the current lags, the applied voltage, VA by 90 degrees. So if you look at this, you say, okay, the power is transferred to the inductor in the form of a magnetic field only when I have positive value of power. So if I look at where do I have positive values of power here, I would say voltage is, current is positive here. Is the voltage positive?
Yes.
So I'd say I'd have 0 there, because volts times amps, it's 0 amps times how many 170 volts would be 0 watts, right? Okay, and then now I'm going to take it at this point, I'm going to say whatever value that is, that must be the maximum value. If the current is at maximum, then that's the highest point in the power waveform. Has to be, because it's the highest point of current compared with voltage. So right there, if I just maybe put him up here, that's where it's at maximum. And then it's at 0 again because the voltage is 0 and the current is at maximum. Yeah.
Somewhat.
Something like that. Best I can do. It's not the best I can.
Teach
I was
him
gonna
how to
check
draw.
to come this one.
It's pretty good.
Okay, I've got negative current and positive voltage. What's a positive times a negative? Negative. You're going to end up with that. So at this point, this power here is transferred to the inductor. To inductor. This one here, previous to that, power back to the source.
Yeah, pretty much.
Okay. Positive and negative, that means I got another negative, and when any one of them is 0, then it's 0 at these points, so it has to be like this, and like this. So there, again, to the inductor, this is back to the source, because we picked one, we picked a side, any side, we said this is to the load, not the load, this is to the inductor, this is back to the source. Are each of these equal to each other in average value, let's say? Yeah, so all the positives and negatives, what's the average of that waveform though?
600 watts.
No, the average of this
0.
is 0. All the positives cancel out the negatives. We call this wattless power. Wattless.
What?
We know we need energy to store into the inductor, but the amount of watts that we use in the circuit is still 0. There's no energy dissipation. If there's a small bit of resistance in here, then you'll feel this getting warm, or whatever, because it has a resistance portion. But if in a pure inductor, wattless, right? Another name for that is quadrature power or reactive power. So I'll write that in here. Quadrature power is the other one. reactive power. You've heard that one?
I have heard that one.
Yeah. 0 watts. Okay, and that's really in a nutshell what this is talking about. And they give you this right here.
I saw a TV show about an anthill inside of that shell. It's pretty cool. Crazy.
So what's true power?
Cool. There's some more of that shit done. Crazy.
This is true power.
Who's that?
Or active. So if you're always out of sync on the wire pull, there's no action. The wire is staying where it is. It's like, it's not going anywhere. Coffee time comes, and you still don't have that wire pull done. Because you're wattless. You haven't moved it anywhere. There needs work to be done for there to be watts happening, right? Active power means everything went great. All the current worked with the voltage. Everything was great. So that's kind of the thinking behind this, guys. We call those bars and all that. Q factor of a coil. It says this will be important to you later. Important, let's put now. It's a ratio of its inductive reactance to its resistance. The Q factor, the quality factor, I guess you could say. Q of a coil, XL over R. We will study this with examples later. So when it says later, it's true, but you gotta know what it, like you gotta know this. So if I say that this is not a pure inductor, that it has 1 ohm of resistance. So if I say R of the coil is 1 ohm, XL is 12 ohms, then what is the Q factor of that coil? I just gave you those two numbers. You got to remember it. XL is on the top. Actually, it's the same as the other one, L over R. You could remember that. It's XL over R. That helps you. That helps you. I'm trying to find ways to remember stuff. So what? What do you do? For this coil, if I said that had 1 ohm of resistance in it, with wires resistance or something, 12 over 1 equals 12. No units. Because it's ohms over ohms, so the ohms cancel, right? How do you make a wire-wound resistor? If you wind a nichrome wire that has a bunch of resistance into a coil, isn't it going to create an inductor? It would, if you wound it the same way. So what they do is they take the wire at one end, split it in half, make a loop at one end, and that's the middle of the circuit actually, and then they wind that. So what's going to happen is all the current going through is going to come back, and the two fields will cancel each other out, and you won't have any inductive effect in that. So you can make a wire-wound resistor that way without having an inductor out of it, because that's what would happen if you didn't do that. And the other one's saturable reactors. Okay, let's try this one. This is what I was talking about.
Same concept.
What you do is you give it a DC current, you fill it with flux. And then you can use this AC coil in addition to the DC level that you've put on there for the magnetism. So there's only a little bit of permeability left in the core. You can adjust that. So they call that a saturable reactor. It's to vary it. So what you can do is you can use a very small DC current to control how much AC current you have. Because think about this. If I make the permeability lower, right? Let's get rid of one of these things here.
No, I'm not done.
Okay, get rid of this one.
No.
Pick the best one. Okay. What is the formula for, this maybe for the quiz tomorrow, what is the formula for inductance?
E over changes.
Delta I over delta T.
No,
What is that?
the property of inductance.
Delta I over delta T.
Like the P property.
The
P
N
How is this built?
N squared.
N squared.
Divided A over.
Yeah. It was the other one.
Everybody talking about over length in meters.
Loud noises.
So, if I can saturate the core in this one by causing more DC current with the rheostat through this DC current here, I'm filling it with flux lines, I've decreased the remaining permeability in that core, I'm actually decreasing the permeability, I'm decreasing the inductance. So what happens to the XL in the circuit? XL is 2 pi FL. Oh, I remember that one. Okay, we did that there, I'm coming back to it. So if I decrease the permeability, I decrease the inductance. So now let's transfer that thought down to this guy over here and say, okay, that inductance just went down. That's the same inductance because of permeability, I've saturated the core. So that means what happens to the reactance of that circuit?
It also goes down.
It also goes down. If the reactance goes down, hang on.
Yeah. Excellent.
Across the inductor I have the reactance going down. What happens to the current? That same reactance there has gone down. So that happens to the current in the circuit, it goes up. So the result is that by controlling this permeability, by increasing the current through the DC coil and increasing the current through the AC circuit attached to the same coil. It's all connected. Anyway, been through this a few times. Okay, let's do this one formula really quick example before we go, because you've got lots of practice stuff. This one here. I'm going to change this to 120 hertz.
No, don't do it.
So this guy here, change frequency to 120 hertz. Easy example. What is the inductive reactance now?
2 pi times.
Double. So what do I do?
Second function 3.
Okay, what you should do, what you should do is get the inductance, there is a short way, but get the inductance of the circuit. So the inductance of this circuit is XL over what? R. 2 pi F.
Holy moly.
Right? I'm just translating, I want L. Is that correct? Yes?
L's inductance, XL's reactance.
Okay, what did we have for reactance in the circuit? We had 12 ohms.
Okay, 12.
Okay, so let's put 12 ohms divided by 2 pi times 60 hertz, because I told you this was at 60 hertz.
But you changed it.
120.
No, but we gotta get the inductance of the circuit.
Oh.
It's almost like you gotta get the resistance of a circuit before you put it into this new circuit, right?
114,
114.159
159.
millihenries?
No, just
0.59.
No, just 59.
And that's millihenries?
That's millis.
Can we put it into henries? 0.11459?
Yeah.
Yes.
Okay, so take that number,
Take it.
plug that in, because that's your constant value that doesn't change because of the way the coil is built, right? The core, XL equals 2 pi FL equals 2 pi times, well, how many hertz now? 120 hertz. times by 0.11459 henries gives me,
Very small.
Error.
did we screw up? 12 divided by 2 pi divided by 60 is
Why positive?
86.39.
okay, so this is wrong.
Yeah.
It's fired. New
Show
number?
if I work, so I get 0.5.
So what is it, 0.3? I do these for a reason because you can see the pitfalls of what you're doing in your calculator sometimes.
No kidding.
0.03183098.
Okay, 0.3, sorry.
Slow down.
You lost me at 0.3.
You had me at
0.32, I guess.
8,
3,
3,
0,
0,
9.
9. Is those the sign language numbers? That's good enough. Okay, Andrew, I'm going to just say that's good enough. You got lots of decimal places there. Okay, take that number, put it in there, all right? And something like that. What do you got now? You should have 24 ohms.
If you don't open bracket, because again, this is going to divide this number, then you divide by 6.
23.97.
It's 20. Anyway.
It's always like they go dividing.
I doubled the frequency, so what did I do to the in reactance? If I double the frequency, that's an easy way to do it. Where are we here? Double the frequency, double the ohms. So you can do it that way too, right? Yeah. It's just I'm showing you how to plug things in. If you don't have the inductance, get the inductance and solve that way. So what's the current in the circuit then? Has it gone up or gone down?
Divide.
What do we have?
We have 130.
Half and half.
XL is 24 ohms. The voltage is 120. The amps is
12.
5. So the new amps are 5. But the reason why I did this is because now you can go on your own and work on it. And I won't have to like explain it all like over a long period. I can just help you where you need it. Okay?
Do you have more worksheet or not?
You have worksheets. The extra worksheets you have already.
Yeah.